So example 8. We paused here from last day. It says, what impulse, oh, I think I'm going to start, this is not a conservation of momentum. Sum of all momentum initial equals sum of all momentum final. It's going to be an impulse question. Must be imparted to a 145-gram baseball to change its velocity from 40 meters per second south to 50 meters per second north. Okay. What are they asking me to find? Impulse. What's another word for impulse? So they're asking me to find that. Now there's two ways I can find that. Change in momentum equals mass change in velocity, final minus initial, and it equals force change in time. Which one am I going to use for A? Well, I'm seeing, I think you clearly with me, Sam, you see a change in velocity. I think I'm going to say this. The change in momentum is going to be final momentum minus initial momentum. By the way, you could have a constant velocity and a changing mass. That's also an impulse. We won't look at that this year, but that's a classic physics first-year university with calculus question. Equals. All right. Can I do this? What's the mass? Please don't say 145, because it's not. 0.145. Okay. What's the final velocity? $50 minus. Oh, you said the mass was 0.145. What's the initial velocity? 40's wrong. Why negative 40? Okay, we have to, as soon as we're doing momentum, it's this unit, you've got to start keeping a sharp eye out for directions. By the way, Elijah, you could have said V final was negative 50. You could have called north negative. There's no rule that says north has to be positive. I probably would have let the initial be negative just because that gives me a lovely minus, which is a plus, and I know when I make dumb mistakes it's with negative numbers. I get a change in momentum, an impulse of 0.145 times 50 minus 0.145 times negative 40, or I could have just gone plus and dropped the negative. 13.1. 13.1, what? Units. Kilogram meters per second. Or Newton seconds. I'd take both, but Race, since I used mass and velocity to calculate it, I'll probably write the mass velocity units. It's just what's in my brain. B. Claire, what's B asking me to find? Oh, what did we just find? Is there an equation that has force and impulse? Yeah. I think we also have this. The impulse equals force change in time. Oh, how about I actually put the impulse? I just wrote a delta. There we go. Oh, wait a minute. Vector. I'm being very careful. I won't take marks off if you don't put a vector sign. The marks will take themselves off because you'll forget and do scalar math. So Neve, I'm being really paranoid saying label, vector, direction. As you already noticed on the part A, you did hear a bunch of people when I said, hey, what's the initial velocity, say 40. And then they caught themselves. Negative, oops. So we'll try and prevent that from happening. What did you say we're finding, Claire? How would I get the force by itself? And time is a scalar, so that division just works like normal math. The force is going to be, it's going to be 13 point, what was it, 05? Yeah, divided by, what's the time? Please don't say 1. 1 what? It's 1 millisecond, which is 0.00, which is 2 zeros and a 1. You know what? The quick way I know is I know that you can replace a milli with a 10 to the negative 3, which I think does end up being 2 zeros and a 1 after the decimal. You like that? Yeah. How do we think of you? As a 10 to the negative 3. My name's a metric prefix. What would be awesome is if someday you marry someone whose last name is meter, because then your last name would be millimeter, because you put a hyphen I. Wouldn't that be awesome? Or any kind of a unit. Wouldn't just have to be meter. You could, liter, pound, anything, and you could have a metric prefix as long as the last name was some kind of a measurement. That'd be awesome. Oh, you know what? That's got to be your first question when you're dating or something like, let's see, I write the name. Oh, no, I got to pass on you. That doesn't work at all. Oh, that makes interesting, right? That would be the Sheldon Cooper strategy of dating and arrangement, right? 13.05 divided by 1 negative 3. 13,500 newtons. Which seems about right. I tried to make up reasonable numbers here. I figure a pitcher pitches, 40 meters per second. If you double that, that's roughly miles an hour. It's about 85, 90 miles an hour, which is what a major league pitcher does. I think when the batter hits it, it does go back in the opposite direction faster than the way it came in. 13,050. Yeah, I got the 5 and the 0 mixed up. Imagine me getting 2 digits mixed up. That would frustrate the heck out of me if I had done that like on a test or something. Just saying. If I had most of it right, but just a little bit wrong, and my friend pointed that out, preventing me from getting perfect. There's a good story there. Wait a minute. That's 4 sig figs, Mr. Dueck. Good point, Cliff. Technically that, right? 13,100 newtons, if you really want to be fussy. 13,000 newtons, well, you know what? Getting hit by a baseball bat would probably, if it got hit on the chest, would probably break ribs, and that's a fairly high force. I think my numbers are good. I was trying to make up reasonable numbers, was my point, Cliff, before you commented that I made a mistake. Okay? Do you see how, even though technically it did say the word collision, do you see how actually we didn't need to use conservation of momentum because we started out in impulse land? Example 9. A 2,000 kilogram car traveling 15 meters per second rear ends another car. Okay, this is a collision. The second car was initially moving at 6 meters per second in the same direction. What's their common velocity if they lock together during the impact? Is there a collision? This is a job for conservation of momentum. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. Do you see any angles, any north of south, any east of west, any thetas, any degrees anywhere? No? Then we can solve this basically using high school math by letting one direction be positive and one direction be negative. We're okay. Before the collision, what's moving? Car 1, car 2, or both? Both. Stuck together or separate before the collision? Separate. So it's going to look like this. Momentum of car 1 before initial plus momentum of car 2 before initial. Bam! They collide. It's going to be a long unit, folks. After the collision, what's moving? Car 1, car 2, or both? Both. Stuck together or separate? Okay. Momentum. Hey, what if they were separate? Then I would have momentum 1 final plus momentum 2 final. And I'd probably have enough information that I'd be good. Momentum is what times what? So this is going to be M1 V1 initial, put a vector, be careful with direction, plus M2 V2 initial, put a vector, be careful with direction, equals the mass of both V final, careful with direction. How many of you have ever been in an accident where you were rear-ended? Okay, or you've seen them in the movies? I'm pretty sure we're talking, look up about something like this. I think if we call the original direction positive, I'm pretty sure our final velocity is going to be positive. I can't see how you can get rear-ended and bounce that way. The physics just doesn't work for me. I don't think you can get rear-ended and have both cars stick together and bounce backwards. I could see how if this was a tank and a little Austin, and the Austin rear-ended the tank, I can see how the Austin could bounce backwards and the tank only move forwards just slightly. But the fact that they stuck together, I think you have a positive velocity incoming. You're going to have a positive velocity outgoing. You agree with me? So I'm just trying to visualize. All right. Hey, Josh, what's this asking me to find?
Common velocity.
Did they say any north to south or any angles? Then I can get the V final by itself with straight generic math by, how could I get the V final by itself? How could I get the V final by itself? Divide by the bracket. So I think the final velocity, the common velocity as I called it, is going to be M1 V1 initial plus M2 V2 initial, all divided by, all right, M1, 2,000. V1, 15. Positive or negative? I think we're okay with positive. Plus M2, 1,000. V2, positive or negative? It does say same direction. By the way, you could have made all of these negative and still got the right answer. You'd just be assuming that for some reason they were traveling to the left or backwards or whatever. Over, can I add M1 and M2 in my head and just get 3,000? Do you mind if I do that? Oh, I think I can do this in my head. It's going to be 30,000 plus 6,000. It's going to be 36,000 divided by 12,000? 12. I mean, that's what I meant to say. 12? Forgot to drop the zeros. 12 what? Meters per second. I'll even put a little positive there to say to myself, in the same direction. In the same direction. Example 10. 2 eggs are dropped from a height h. One hits the floor and breaks. The second one falls in a pail of water and survives. What's the main reason the second egg survives? Using principles of physics. Convince me. How many of you have ever done an egg toss where you've played catch with an egg as you move further and further back? Okay. Nate, you had a suggestion.
Well, with the one with the water, I think you're increasing the time, so the sparks from there, the water has to be smaller.
I think he's right. We're going to write that mathematically, but let me pause for a second. I would probably say something like this. Same mass. Same VI because it's dropped. VI is 0. Same V final because it's the same height. Therefore, same They both go through the same change in momentum. So what was your argument, Nate?
If you increase the time, it works out.
So another expression for change in momentum is force change in time. Egg 1, we have this. Big force, small time. There's egg number 1. Egg 2, we have same change in momentum. But what did you say we made bigger, Nate? Big change in time, much smaller force. Is that okay, writing it that way with big letters and small letters? I don't know. You could write it out in English too, but... Okay. Hey, there's the physics of seatbelts as well. They want you to move forward a little bit before they bring you to a stop, because if I can lengthen the collision effect on your body, if I can make it 2 or 3 times as long, good stuff. It explains on most concrete barriers, for example, by the Pitt Bridge, they have those water garbage cans, those water-filled garbage cans. What are those designed to do? Lengthen the collision. Because in any collision, your change in momentum is the same. In fact, all of you have gone through a change in momentum that would be terminal, because you've all started on the freeway and ended up at rest. But as long as you spread it out over a long time, no problem. It's the time, the force, the acceleration that does the damage. If we look at a graph of force versus time for the egg hitting the floor, it might look as follows. By the way, where does that appear on this graph? Remember the graphing tricks that I showed you? It's either going to be the slope or it's going to be the area. Which one? And convince me.
Area.
Why?
Because force time is all. Multiplication of the area.
So the impulse, the change in momentum, is that there. It says, which of the following graphs, A, B, or C, would best represent the force time graph for an egg hitting the water? The egg on the floor is shown, graph is shown as a dashed line for comparison purposes. I don't think it appears as a dashed line on yours anymore, does it? No. I've told you, this was typed in Word 95 for Mac. We're now 2014, so, and I can't edit the pictures anymore. I will slowly start redrawing these by hand, but it's going to take a while. First of all, should the force be the same height, higher, or lower as the original? Lower. Why? Oh, time. Should time be the same width, higher, or narrower? Wider, longer. Okay, I'm looking for a graph that's not as high and much wider. So, agree? Now, then the question is B or C. Well, look at those two. They would have to have the same area as graph 1 because the change in momentum is the area under the graph. So kind of eyeball what the area of this first graph is and ask which of those two best matches it. You know what? This is where, sadly, I love this question, except the graphics are finally breaking down. I'm not sure whether it's B or C. I'd need some kind of a scale with some numbers to be more accurate so that I could actually make a guess as to roughly what the area of my original triangle was. What do you guys think? B or C? What has about the same area as this big, tall, skinny graph? You guys think B? I think so too. I'm not now C has a really low force. I'm just not convinced. Oh, because it's taking the same amount of time as B, I'm not convinced. It's got the same width. I'm not convinced it has enough height to fit in the whole area. But I can't quite be positive, Alex, because this graphic is slowly breaking down over the years. But I like the thought question still, because, hey, replace eggs with seatbelts, replace eggs with crumple zones on cars. All crumple zones on cars are designed to do is make the collision last a little longer. It says explain your answer using appropriate physics concepts. I think we just did. Homework. Number 1, 2, 3, 4, 5 is good. 6 is good. Jet engines are great examples of momentum. 7 is a nice review from last unit. Because energy is conserved, all of the energy stuff is still fair game in this unit, because we're eventually going to start looking at questions where both energy and momentum is conserved, and you use part of one to find some information for the other, and then part of the other to find some information for the one. So I did just assign, number 7 is a work energy question. Eight is good. 12 is good. You assigned everything. Well, no, I'm pretty sure I skipped 9, 10, and 11 because I don't see them here. Little whiners. A couple of videos before I